So let's take the question number 6. The question there says we should solve the differential equation I. We have the square y over the x square plus 7 dy dx plus 12y equal to exponential 5x. And the second one there is x dy equal to y plus 1 dx. Now, the first one we have is a linear non-homogeneous ordinary differential equation. It is non-homogeneous because to the right hand side we have a function of x. If we equate the left hand side to be equal to 0, then the differential equation becomes homogeneous. But since what we have here in the question, the right hand side is equal to a function of x exponential 5x, so this differential equation becomes a linear non-homogeneous ordinary differential equation. So let's see how we can solve this given differential equation. And of course, this question is 10 marks. So we have the first question there, I, the square y over the x square plus 7 dy dx plus 12y equal to exponential 5x. So, having known that this differential equation is a linear non-homogeneous ordinary differential equation, the solution to any differential equation of this form is given by y equal to the complementary solution y sub c plus the particular solution y sub p. So we have to find the complementary solution and find the particular solution, then add them together to find the general solution of this differential equation. So the question now is, what is the complementary solution and how can we find the complementary solution? To find the complementary solution, you always assume you let y to be equal to exponential mx. So what you have to do here is to find the value of m, and m is the root of that given differential equation. So if you know the value of m, then you can find the complementary solution. So what we are going to do, we have y already to be equal to exponential mx, so we have to substitute y here. In place of y, we substitute exponential mx, but then we don't know the y dx, and we don't know the second derivative of y with respect to x. So from here, we can find the y dx here as follows. So if we differentiate y with respect to x from here, we have, remember to differentiate an exponential function, you take the derivative of the index and multiply it by the function. And the derivative of the index here is m, because if you differentiate mx with respect to x, you have m. So you write to m, and then you rewrite the function exponential mx. So this becomes our dy dx. But also, we also need the square y over dx square, which is the second derivative. So it means that we have to differentiate y again. So we have to differentiate dy dx with respect to x again, and this will give us the square y over the x square, and this should be equal to, if you differentiate this, because m is a constant, so if you differentiate mx again, you have m. So what you have here is m times m exponential mx, and this should be equal to m square exponential mx. So since we have obtained the value for the square y over the x square, dy dx, and y, we can substitute it back into the given differential equation. So let's call this equation 1. So we are going to substitute into equation 1. So if we should substitute into equation 1, we have the square y over the x square, and which is m square exponential x. So we have m square exponential mx plus, we have 7 dy dx. and our dy dx is m exponential mx. So we have 7 into m exponential mx plus 12y, and our y is exponential mx, and this is equal to the right hand side we have exponential 5x. So this is what we have. So the next thing we want to do is, we have exponential mx here, we have exponential mx, we have exponential mx. So we can easily factorize exponential mx. So what we have here is exponential mx into, if you remove exponential mx here, you have m square. If you remove exponential mx here, you have plus 7m plus 12 equal to exponential 5x. Now, to obtain the complementary solution, we need to set the left-hand side to be equal to 0. To obtain the complementary solution, we set this left-hand side to be equal to 0. So if we should set the left-hand side to be equal to 0, we have m squared plus 7m plus 12 being equal to 0. And of course, exponential mx is supposed to be equal to 0, but we are not going to set exponential mx to be equal to 0, because exponential mx is the solution of that differential equation. So we only set the root m squared plus 7m plus 12 to be equal to 0, just to find the complementary solution y sub c. So if we set this to be equal to 0, we can easily factorize this. So let's factorize this. We have m into m plus 3 plus 4 into m plus 3 being equal to 0. Remember how we factorize it? You look for two numbers such that if you multiply, it gives you 12, and if you add, it gives you 7. So those numbers are 3 and 4, because 4 times 3 will give you 12, and 4 plus 3 will give you 7. So let's factorize this complete. We have m plus 3 into m plus 4 being equal to 0, which means that our m is either equal to 3, or our m is either equal to minus 3 or minus 4. From here, it means that we have m to be equal to minus 3 and m equal to minus 4. So we can call the first m1 to be equal to minus 3, and m2 to be equal to minus 4. So this is what we have. But we said that y is equal to exponential mx. So you recall, but y is equal to exponential mx. So this means that y1 should be equal to exponential m1x, and y2 should be equal to exponential m2x. So our y1 becomes exponential m1 is minus 3 minus 3x. Then our y2 becomes exponential minus 4x. So since we have obtained the values for y1 and y2, then we can find our complementary solution. Remember, the general solution is y equal to the complementary solution plus the particular solution, which is given as y sub p. So y sub c becomes c1y1 plus c2y2. C1 and C2 are arbitrary constants, so we don't need to worry ourselves about C1 and C2. They are just constants which we can use to find the differential equation back if we are to form a differential equation. So the only thing we need, just know this pattern. If you have two solutions, y1, y2, so it becomes C1 y1 plus C2 y2. If you have three solutions, it becomes C1 y1 plus C2 y2 plus C3 y3, and so on. So what we have here is y sub c being equal to c1, but our y1 is exponential minus 3x. So we have exponential minus 3x plus c2 exponential minus 4x. So this becomes the complementary solution. of that given differential equation. So the next we have to find is the particular solution, then add them together to find the complete solution of that given differential equation. So to find the complementary solution, always know that you let y to be equal to exponential mx first, and then you differentiate y with respect to x, and you differentiate it again, and then you substitute back into the given question and factorize exponential mx. Then you set the root to be equal to 0, which is m squared plus 7m plus 12. You set it to be equal to 0, and you factorize to obtain the two roots. Then you come back and recall that y is equal to exponential mx. So it then means that y1 should be equal to exponential m1x, y2 should be equal to exponential m2x. If you have three roots, then it means you are going to have y3 to be equal to exponential m3x, and so on. So having done that, you substitute the roots, and your y sub c becomes the first arbitrary constant times y1 plus the second arbitrary constant times y2. If you have y3, the next one becomes plus the third arbitrary constant times y3. And then you plug in the values for y1 and y2, and you get your complementary solution. Then the next one now is to find the particular solution, to find y sub p. Now, how can we find y sub p? Let's quickly see how we can find y sub p. Recall that the given differential equation was d square y over the x square plus 7 dy dx, plus 12y being equal to exponential 5x. So this was the given differential equation. So to find y sub p, now you let y to be equal to what you have on the right hand side. You let y to be equal to what you have on the right hand side, which is exponential 5x. Remember, to find y sub c, we equate the left hand side to be equal to 0. But now, to find y sub p, we equate y to be equal to exponential 5x. But we need to attach an arbitrary constant, which we are going to find the value of that constant. And we say let that constant be a. So the first thing you need to do to find the particular solution, y sub p, you let y to be equal to what you have on the right hand side, which is exponential 5s. So we said for you to find the particular solution, you set y to be equal to the right hand side. If the right hand side is exponential 5x, you multiply it by a. So you have y to be equal to a exponential 5x. Please take note, this is only valid if the right hand side is an exponential function. But if the right hand side is a quadratic function or a trigonometric function, then this particular solution will not be in this form. So if you want to know the form of how the particular solution will be if the right hand side is not an exponential function, I'm going to send the link of that video in the description so you can check that out to know how to solve that given type of problem. So now we have y to be equal to a exponential 5x. So what you need to do now is to just attach p as the subscript. So you just have y sub p being equal to a exponential 5x. We need to find dy dx from here and find the square y over the x square from here also. So our y already is a exponential 5x. So our dy dx is what we want to find. So dy dx, remember this is y. So our dy dx simply means differentiate this. So if you differentiate this, you have a is a constant and 5 is a constant. So we need to differentiate the index, which will give us 5, and multiply it by the function. So we have 5a exponential 5x. Then the next we need to find is the square y over the x square. So we have the square y over the x square to be equal to, it means we need to differentiate this again. So if you differentiate this, you have 5 times 5 a exponential 5x, and this should be equal to 25a exponential 5x. So having find the square y over dx square, the next thing is to substitute it back into the differential equation given to us. And now take note, the reason why we are doing all this is just to find the value of a, because we have already said that the particular solution is a exponential 5x. So if we add this value to what we obtain in y sub c, we get the general solution, but then we don't know what a is. A is a constant, so we need to find the value of that constant. That is the reason why we have to substitute this into the differential equation. So if you should substitute the square y over the x square, the y dx, and y back to the differential equation, you have 25a exponential 5x plus 7, the y dx is 5a exponential 5x. So you have 7 times 5a exponential 5x. Then the next one you have is 12 plus 12y. But our y now is a exponential 5x. So we have a exponential 5x. And this is equal to the right hand side. We have exponential 5x. So what we are going to have here is, if you should observe, we have 25 here. 7 times 5 will give us 35 plus 12. So we have 25 plus 35 plus 12, and that should give us 72. So what we have here is 72a exponential 5x being equal to exponential 5x. Please take note, I add them together because they are the same. This is a, this is a, this is a. This is exponential 5x, exponential 5x, and exponential 5x. So what you need to do is to add their coefficient, which is 25 plus 35, which is 7 times 5 plus 12, and that will give us 72. Then a exponential 5x, and this is equal to the right hand side, which is exponential 5x. So the next thing we need to do is to make a subject of formula from here. So if you make a subject of formula, you have a to be equal to exponential 5x over 72 exponential 5x. So if you observe, exponential 5x will cancel out. So what you have here is 1 over 72 as the value of your a. But remember that your y sub p is equal to a exponential 5x. So you need to substitute the value of a back to your particular solution and find the answer. So from here, we are going to have y sub p to be equal to a. Our a now is 1 over 72. So we have 1 over 72, then exponential 5x. And that becomes the answer to our y sub p. But recall that your general solution is y equal to y sub c plus y sub p. So let's add them together and find the answer to that given question. All right. So we said that the solution is y equal to y sub c plus y sub p. So we have y being equal to y sub c is this. This is our y sub c. So we have c1 exponential minus 3x plus c2 exponential minus 4x, which is our y sub c. Then the next one is our y sub p. And we obtain our y sub p to be 1 over 72 exponential 5x. So we have plus 1 over 72 exponential 5x. And that becomes the solution to that given differential equation. Alright, so this is the second part of that question. We are asked to find the solution of the differential equation x dy equal to y plus 1 dx. So how can we solve this form of differential equation? Now we need to know here that this differential equation is first order differential equation, because we just have dy dx. So for us to solve this differential equation, x dy equal to y plus 1 dx. Because we just have the first order dy dx, not the square y over the x square. So we are going to be applying the variable separable method. So we are going to use the variable separable here. So I'm going to state it using the separation of variable. So using the separation of variable method, we just have x dy equal to y plus 1 dx. So all we need to do is to just, because we have dy here, we bring y term to the left hand side, and because we have dx here, we bring x term to the right hand side. So that's just the idea about variable separable. If you have dy here, you bring all the term containing dy to that side. If you have dy this side, you bring all the term containing dy to that left hand side. So in this given question, we have dy here. So what we need to do is dy, then we bring the term containing dy, and the term here is, sorry, we bring the term containing y, and the term here is y plus 1. So for us to bring y plus 1 to the left hand side, we need to divide both sides by y plus 1. So we have y plus 1 here, and this is being equal to the x. So we need to bring x to the right hand side, and to bring x to the right hand side, we need to divide both sides by x, so that we have x here. Now to find the solution, now we need to integrate both sides. We integrate both sides. Now if you integrate y plus 1, you are going to have the natural log of y plus 1. So if you want to know how, you can also comment below, then I'm going to give the link of that video to see how we can integrate this given function. So if you integrate y plus 1, you have the natural log of y plus 1. To the left hand side, to the right hand side, if you integrate 1 over x with respect to x, you have the natural log of x. Please take note. If you integrate 1 over y plus 1, you have the natural log of y plus 1. If you integrate 1 over x, you have the natural log of x, which is the same thing as ln y plus 1 equal to ln x. But because this is an indefinite integral, so we need to add a constant plus c. And this becomes the solution of that given differential equation. So that is how to solve this given question using the variable separable method. So the first thing you have to do there is to state that you are using the separation of variable method. And the next one you have to do is the term containing y, you bring it to the dy side, and the term containing x, you bring it to the dx side. So to this side, we have y plus 1. So we have to bring y plus 1 this side. And to bring it, we divide both sides by y plus 1. And we send x this side, which by dividing both sides by x. So we have this. Then the next thing we have to do again is to integrate both sides. If you integrate 1 over y plus 1 with respect to y, you have ln y plus 1. If you integrate 1 over x with respect to x, you have ln x, and then you add your constants, and that becomes the solution of that given differential equation.